Hello everyone. Let's take a look at our next problem. The simultaneous equations in x and y, cos theta x minus sine theta y equals 2, sine theta x plus cos theta y equals 1, are solvable for all values of theta in the range 0 to 2 pi, except for one value of theta in the range 0 to 2 pi, except for two values, or except for three values. Okay, so basically we're just trying to find not necessarily for which values of theta the system can be solved, but for how many different values of theta this can be solved. Now, of course, looking at this system, it's a linear system in x and y. And so if we think of the matrix of coefficients, we're basically just trying to find when that matrix is invertible. The only thing, if it's not invertible, do we have a solution? If it's not invertible, it's potential that we have an infinite number of solutions, right? I suppose we'll have to think about that. If it's invertible, certainly there's a solution. You know what we could do is just solve for x and y, and then see what happens for various values of theta. So my two first thoughts here are to think of this matrix, compute its determinant, and see when it's equal to 0 or when it's not equal to 0. And the other is to just explicitly solve for x and y. You know, do the algebra in terms of sine theta and cos theta, and you know, there will be times when we'll have to divide by something that has a sine theta or a cos theta in it or something like that. But yeah, what will happen if that might be a better way to go, actually, because then we might explicitly see, you know, if the determinant of that matrix is equal to 0, it's possible that we have an infinite number of solutions. But I'm thinking that if we just try and explicitly solve for x and y instead, we'll see that. So if the determinant is 0, there's either an infinite number of solutions or no solutions. And I think by just explicitly solving for x and y, we'll see probably, maybe, that we would instead have 0 solutions. You know, another way of thinking about this is to recognize that the matrix of coefficients here corresponds to a rotation of the vector xy in the plane. And it's a rotation by an angle of theta. I think that's correct. I'd have to think for a second. I'd have to refresh my memory on exactly what the rotation matrix form is, but it's something like this. Let me write down what the matrix is I'm talking about exactly. Maybe this is a more straightforward, easy way of doing this. Again, I just don't remember exactly what the form of the rotation matrix is. I know it's filled with sines and cosines, and there's a negative sign in there somewhere. But we could figure that out by, you know, figuring out what happens to the standard unit vectors. Yeah, so this is a rotation matrix. It rotates a vector counterclockwise by an angle of theta. If we look at the coordinates, you know, the matrix multiplied by the first unit vector gives us cos theta sine theta, which is a point here, and a matrix multiplied by the second unit vector along the vertical axis gives us these coordinates, which is something over here. And so, you know, rotation matrix can always be inverted just by rotating by an angle of negative theta, rotating it back. So if we have an image vector, which is 2, 1, we just rotate that by an angle of negative theta, and we'll get the original vector xy. So what I'm going to do here actually is just show that this matrix is always invertible. And I'll do this by multiplying by what I claim is the inverse, which is cosine of negative theta times negative sine of negative theta, sine of negative theta, cosine of negative theta. These, of course, a lot of these things simplify by using properties of trig functions, symmetries of trig functions, like that. So cos is an even function, sine is an odd function. And if I work out all the multiplications here, so I've just done the 2 by 2 matrix multiplication of everything, and we use some trig identities. The Pythagorean identity shows that the top left and bottom right element are 1. The top right and bottom left element are both 0, so we get the identity, right? So this shows that our original matrix M here is invertible, and the inverse is exactly M except with theta replaced by negative theta. And that shows that this system will always have a solution. So for all values of theta in the range 0 to 2 pi. Yeah, this would have been a lot easier if I had just gone directly for the, by recognizing that this thing was a rotation. The other techniques would have worked, right? If I had just taken the determinant of this matrix and shown that it's equal to, that it's not equal to 0. In fact, just look at the matrix M. The determinant is equal to 1, which is expected for a rotation matrix because it doesn't stretch anything in any direction. Or if I just tried to explicitly solve for x and y in terms of theta, I would have eventually gotten to a point where we always had a solution. So that's our answer. This can be solved for all values of 0 to 2 pi. If I have any more comments about this one, or if I find some kind of mistake, I'll put it in the description below. Otherwise, thanks for watching.